Recently in one of my weekly live streams, which I do every Monday night at 5 o'clock Pacific time, I talked about how to find inflection points of a function. First, I actually started with how to find the second derivative of the function and then use that to find inflection points. But in this video, I'm going to be assuming that you're comfortable with finding the second derivative of a function, and we're going to pick up at the inflection point portion. If you do want a little refresher on second derivatives and how to find them, just go ahead and click on that right up there and come back to this video and we'll talk about inflection points. Anyway, let's go ahead and jump into the content and I'll show you that clip from that weekly live stream where I talked about inflection points and how to actually find them. Okay, so now what we're going to do is we're going to use that second derivative to find the intervals of concavity and the inflection points. So before we kind of get into that, there is one thing I want to kind of point out, which is a little bit odd when it comes to inflection points and what the definition of an inflection point is. So essentially, inflection points, I've seen them kind of defined a couple different ways. They all basically get at the same thing though, which is an inflection point occurs when you have some spot on your function where it switches from being concave up to concave down. So like basically right here, it's concave up. Right here, it switches to concave down. So in other words, it's curving upwards and it switches to curving downwards, or vice versa, right? If you're concave down and then you switch to concave up, that point where you switch concavity, that would be an inflection point. Now, this kind of relies on the function actually being continuous around that point. So what I mean by that is, let's say we have like a vertical asymptote of a function, okay? And we are concave up to the left of it, creating this vertical asymptote, and then we're concave down to the right of it, creating a vertical asymptote. This x value right here wouldn't really be an inflection point though. And it's kind of weird. It basically switches from concave up to concave down, but there's not actually a point on our function at this spot. So basically what we need in order for something to technically be considered an inflection point is we need our original function to actually exist there. So really we're looking for inflection points specifically within the domain of our original function. Now, in this case, this function here is not going to have a vertical asymptote. And in fact, looking at it, what we have is a polynomial. So polynomials have a domain of all real numbers. So this original function, h of x, has a domain of all real numbers. That's what this symbol means here, just all real numbers. What that means is it's continuous everywhere. In other words, any possible x value is within the domain of our function. So there's not going to be a situation where we are like switching from concave up to down or vice versa, but not having an inflection point within this example. Now, the reason why I say this is kind of a weird topic is even though there technically wouldn't be an inflection point on this function right here at this vertical asymptote, you still would want to kind of consider that as an edge or basically an edge of your interval if you're looking for intervals of concavity. So that's why it's weird. We want to kind of treat it as if it's an inflection point and use it like an inflection point as we look for intervals of concavity. But technically it's not an inflection point because we need, inflection points are just going to be points that are within the domain of your original function. So keep that in mind as we kind of continue our discussion of these things here. I'm not going to consider, well, like I said, in this case, our function, its domain is all real numbers. So it's not really going to come up here. But if you're doing other similar examples, you want to keep that in mind because you would want to kind of use spots like that. And I'll get into what exactly that actually looks like here in a second. But you're going to want to use that for the intervals of concavity, but you're not going to want to consider those inflection points technically. Let's get into how to actually find those things with this example. So intervals of concavity and inflection points. Typically, these things are they're tied very closely together, obviously. I like to kind of start with the inflection points, and I'll kind of talk about why in just a second. But basically, the first step in finding inflection points and intervals of concavity is going to be to take your second derivative and set it equal to 0. So basically, we're just going to take this function right here, 20x cubed minus 12x, because that's our second derivative of our function, and we're going to set it equal to 0. And then from there, we're going to solve for x. Okay. So how would we solve a function like this for x? Well, what we can do is whenever you have some sort of equation equaling 0 and you're trying to solve for x, typically a good strategy is to see if you can factor it. So in other words, look for any sort of term that these two things have in common, the 20x cubed and the minus 12x. What do they have in common? Or in other words, what are they both divisible by? Well, they're both divisible by 4, and they're both divisible by x. Okay, so we can basically factor out a 4x out of the left side of our equation here. So if we factor out a 4x, what will that leave each of these terms with? If we take 4x out of this, we're going to take 4 out. We're going to be left with a 5, because 4 times 5 is 20. And then if we pull an x out of an x cubed, we're going to be left with x squared, because x cubed divided by x is x squared. Okay. And then from minus 12x, if we divide minus 12 by 4, we're left with minus 3. And then if we divide x by x, it doesn't leave us with anything, just a 1. 3 times 1 is just 3. So basically that's what's going to be left. Okay, so whenever you have something factored like this, what you can then do, if you know that you have this kind of factored thing equals 0, what that allows you to do is split this into two separate equations. So we can take each of these parts, each of these factors, and set them equal to 0 by themselves. Because if one of these factors is 0, the product of 0 times anything else is also going to be 0. So we would have 4x equals 0, and 5x squared minus 3 equals 0. Okay, so now we have these two simpler equations which we can solve for x. So in this case, we can divide both sides by 4, just giving us x equals 0. Over here, we can add 3 to both sides. Then we can divide both sides by 5. And then we can take the positive and negative square root of both sides. So you do want to be careful with that. You do need to take the positive and negative square root whenever you have x squared equals something. The square root will cancel with the square root over here, but you always need to take the plus and minus square root of whatever you had on the other side of your equation. So we're going to have 3 basically potential inflection points. So like I said earlier, technically we don't know that all 3 of these x values are inflection points yet. However, this basically what we have kind of figured out at this point is our possible list of inflection points. So, you know, a lot of times in calculus, these would all just be considered inflection points. And, you know, I really don't think there's going to be that many situations where your professor or your teacher is going to mark you wrong for saying that these are all inflection points necessarily. But you do want to be careful because technically we don't know that they're inflection points yet. To figure that out, what we're going to want is to find the intervals of concavity, which is the next thing we're going to be talking about here. And we need to make sure that to the left of each of these inflection points, we are either concave up or concave down. And then to the right, we are the opposite. So we need to make sure that we're switching from concave up to concave down or vice versa at these 3 points. And if that's true, then they would be inflection points. And we do also know that because our original function has a domain of all real numbers. So if our domain was limited in some way, you know, if there were some x values that we could not plug into this function, then you would want to be careful of that as well. Because like, let's say, for example, the domain of our function was all x values greater than 0. And we found x equals 0 as basically a possible inflection point. You wouldn't actually want to use that as an inflection point, because if our function is not defined for x less than 0, it's only defined for x greater than 0, or equal to 0, I should say. It's not going to be an inflection point because we can't switch from concave up to concave down at x equals 0 if we know that our function doesn't even exist for x less than 0. But basically that's the idea there. So obviously, like I said, the domain stuff doesn't really come up in this example, but just to kind of give you a tip for other problems you're going to run into, you want to be careful of that. Well, I hope you found this video helpful. If you did and you want to keep taking this topic a little bit further, my next video is going to be showing you how to use the information that we just talked about in this video and kind of build on that to actually talk about and find intervals of concavity of this function. So if you want to take this a little further, come back and learn about intervals of concavity, just go hit that subscribe button and that bell icon down below so you're notified when that next video comes out. If you're not watching this right after it came out, I'll come back and put that video right over there so you can go check that out at a later time. And if you're in that boat and you did find this video helpful, just go ahead and hit that subscribe button down below anyway, because I'll be having lots of other videos that I'm sure you'll also find very helpful coming out in the near future. Thanks, and see you next time.